Hello, welcome to my video 11 in the lecture Advanced Mathematic Modeling. You might have noticed that in the StudIP I have downloaded a PowerPoint presentation where I have all the slides of the lectures. So some of you asked me to do this, so you don't have to when you want to go again over the lectures, don't have to wait for the next slide in the videos. You can directly have an overview of all the slides I showed. In this PowerPoint I also gave some literature hints. So here I have this written down on the paper again. So actually there is not the one book that I can recommend you which contains all the material of the lecture. So this lecture is a selection of stuff from me which I think makes sense. It's in a logical structure. So where I selected, I think, some interesting modern aspects, and so there is no real text like for this, but so some recommendations. So if you want to have a basic knowledge or basic information about probability distribution, so I like this book by David Steersaker, Probability in Random Variables, a Beginner's Guide. So this is maybe a bit elementary from the content, but if you never heard about probabilities and something, so that's a book one can read. A lot of nice exercises, very good descriptions. So when you read this book, you have a fundamental understanding what probabilities and random variables are. The same guy, Steersaker, together with Grimmett, they have also written a more advanced book, Probability in Random Processes, and there is a second book, 1000 Exercises in Probability. This is then, on the other hand, a bit too mathematical with respect to my lecture, so this is much more advanced, and this is a book, it's not so easy to read from begin to end, but a lot of material that I show here in the first half of my lecture you will find also in this book. Another very advanced book is the Feller. That's kind of the Bible for many statistical physicists when they want to look up some theory in probability. So the book is called An Introduction to Probability Theory and Its Applications. So it has 2 volumes, which tells you it's maybe not a book you will read from begin to end. It has a high level, but if you want to know something, you have a certain distribution you want to know, or so, that's a book to look for, to look into. And then here, Manfred Schröder, the book Fractals, Chaos, Power Laws, Minutes from an Infinite Paradise. So that's a book written in very simple terms, where he describes a lot of interesting facts, anecdotes, stories about the topics I want to describe also in my lecture, Fractals and Power Laws. So that's a nice book to read. This is not too advanced, it's more like to get some side material, some very nice interesting applications. And here even a book without equations, like from Geoffrey West, universal, it's called Scale, Universal Law of Life, Growth and Death in Organisms, Cities and Companies. So that's more in layman terms, so a book about things we will cover in the second part of the lecture about scaling and application in metabolic theory in cities and so on. So this is some literature. During the lecture maybe I will give you some other things, but so if you want to read something, so here you have some literature. So okay, where have we been in the last video? In the last video we had discussed a bit, if we have a sample, some data, a sample of a certain size, how can we estimate the mean and standard deviation, and how can we estimate the probability density? And we saw we can basically do it by constructing the histogram. so that we just bin the data and then normalize in the correct way, and then we can reconstruct the histogram. But then I also mentioned histogram building making is an art somehow, because you have to find the right bin size or the distribution of bin sizes, which you might have more densely. So you might have a lot of small bins where there's a lot of data, large bins where there's not so much data. You can even do this systematically with increasing values of the random variable, increasing the bin sizes. So these were things to do histogram, and when you see the examples, the exercises, you will see many examples to learn how to do such histograms in practice. But histogram is not the only way to estimate a PDF, and now I want to show you a second way to construct the PDF, and that's by rank plot. So how do we construct a rank plot? Let's assume this is your sample. So you have your n data points, which give you measurements of your value of your random number x. And we want to know what's the distribution from which these x are drawn. We assume they're taken from such a random process. So in the histogram, what we were doing, we were looking in x, and we're looking which values of x were occur how often. So we had here bins on the x, on the y-axis. So we had here bins and counted the number of points in every bin. Yeah? And in the rank plot, we do something else. We just sort our data. Sort all values in descending order. So what we do, we just plot the same data again, but we look first what's the largest value, and this gets the rank 1. This comes first. And then we look search for the second largest value. This gets rank 2. Third largest value gets rank 3. So we had here this, then we have the fourth largest value. That's rank 4. And so then we continue this until we have all our data points. So we have here a strictly decreasing function, and this plot we call the rank plot. And to better see this, we can connect the points here by line. And then the resulting function, of course, is a representation of the distribution from which the x are taken. So on this axis here we call the rank, because now we have a very specific order in which we take the points. So rank 1, which means is the largest value. In the sample, rank 2 is the second largest value, and so on. So on the computer you can do this very simple. Basically you just make a plot of sort of x. So you need a sorting algorithm. There are very efficient sorting algorithms, and you have to take care. Maybe you have to give some other parameters to your library so that you sort in descending order, because some sorting you can also sort in ascending order, or you sort in ascending order and then just revert the vector, the resulting vector. So it's very simple to construct such a rank plot. Now the question is, what's the connection of this rank plot with our PDF and the histogram? And there is some very simple idea. First, when you compare to the distribution, you see that the x variable here is on the abscissor, on the x-axis, where it's here it's on the ordinate on the y-axis. So we have a reversion of x's. So let's see what's happening if we take our rank plot and just invert the axis. So we take the same plot, but plotted just here the xi and here the rank. So here we go 1, 2, 3 until n, and here was our largest value, second largest, and so on. So it's basically the same plot, but just everything flipped. And now we can look what does the resulting function that we have here what does this resulting function mean if we take it at a certain value x? What does this value here mean? And when you think a little bit, this value here this is because like we count here, so that's the first that's the largest value, second largest, and so on. And so we see here a count, so this gives us the number of all x values in the sample that are larger than our position x. So up to a normalization, this blue curve is the cumulative distribution. This is the distribution p to be larger than x. You remember typically we have given the p smaller than x, the cumulative distribution, which is decaying. So this is just 1 minus p smaller of x. But of course we have to take care with the normalization, because the cumulative distribution is normalized between 0 and 1. So you have to normalize this value by n. When you take this function, because you want this not to be the number of all x values, but the fraction of all x values larger than x. So you have to normalize this by 1 over n. So you see, with the rank plot, we can construct the cumulative distribution. And the cool thing, so rank plot gives us the cumulative distribution. And in comparison to the histogram, no parameters are needed. So that's very cool. Remember, histogram was an art. We have really to find our bins. How big are they? Where is exactly the position of every bin? Here we just sort our data and plot the sorted data. The disadvantage of so why don't we always use rank plots? Why do people do histograms? The problem is this cumulative distributions always look the same. If you want to have real insight in the data, you need the probability density. So we know we need to take a derivative of this function, and when you take the derivative, you have to again find certain intervals in which you numerically take your slopes, and then you have your parameters back. So if you really want to go from the cumulative to the PDF, then we need to put again parameters, and then we can directly construct the histogram. But it's interesting that two very different numeric algorithms, sorting and inverting axis, is numerically equivalent to binning data. But sometimes it's enough to have just a cumulative distribution to get some idea about the distribution of our data, and then the rank plot is very recommended. For example, in ecology, when you have abundance distributions of species, ecologists typically use the rank plot because it's so simple and robust. Okay, that's for estimating parameters. These were techniques that you will need in order to numerically solve the exercises. Okay, thanks for now.